Okay, welcome back, everybody. So this is going to be a fun lecture. We're going to take Fourier Series, which we've defined as kind of a coordinate transformation of functions, and we're going to derive the Fourier Transform, which is a continuous function that exists for almost all normal functions that we think about. And then on Monday, we're going to start looking at properties of the Fourier Transform that might allow us to solve partial differential equations more easily. Okay? I'm going to be out of town next Wednesday and Friday, and then the following Monday is also a school holiday, so you won't see me for 3 lectures. And so I've posted 3 old lectures that I've already recorded on how to do discrete Fourier transforms or fast Fourier transforms in a computer. So these are some of my favorite lectures. They talk about image compression, audio compression, fast Fourier transforms in a computer, and they start to pave the way for actually numerically simulating pretty complicated PDEs in a computer. Okay, so we'll talk more about that kind of on Monday, and then when I get back the following like 4 lectures later. So I just want to show you this video that I made. This is for a paper that I just submitted. Well, sorry, I submitted it a year ago and they just got back to me, which happens unfortunately sometimes. And what we have here is this cool color plot here is essentially some kind of a partial differential equation in the spatial domain. Okay, think of this as space. I like to think of these as like simulated make-believe weather patterns. And I've made it so that the left side always equals the right side, and the bottom always equals the top. And so if you imagine taking this rectangle and gluing together the top and the bottom, you get a tube. Right? If I glue together the top and the bottom, I get a tube. And then if I glue this side to this side, I turn it around, I get a donut. Okay, so if I have periodic boundary conditions top and bottom, left and right, then I map my spatial domain onto a donut. So this is super esoteric. These are make-believe weather patterns on a donut planet. Okay? But the way that I generate these is kind of interesting. So in the frequency domain, in the Fourier Transform domain, I have these same coordinates. And every ij location in this Fourier Transform domain corresponds to a sine wave in x times a sine wave in y at that given frequency. So these are higher frequency sine waves in x and y. These are lower frequency sine waves in x and y. And I take these 5 different frequencies, spatial frequencies, these different ij locations, and I essentially drive them with some kind of an ODE. I have them oscillating and I have them decaying at some slow rate. And I'm plotting the inverse Fourier transform in the real domain. So some of what we're going to be doing in the continuous Fourier integral, in the 3 video recorded lectures for next week, we're going to start to see how we would actually code these up in a computer with discrete Fourier transforms. And you can do some pretty neat things. For example, one thing you can do, imagine that I'm trying to predict the weather on this donut. Okay, but sampling stations are expensive. If I want to actually measure the weather conditions at a location on this donut Earth, it might be really expensive. It might cost me tens of thousands of dollars to build a weather station in Antarctica or in Africa or anywhere. And so maybe I only get to measure at 15 or 20 locations on the surface of this planet. Right? Maybe I only get to measure at 15 or 20 locations in the ocean or in the Gulf of Mexico. Can I back out what the weather looks like at every other point by inferring what these Fourier coefficients are? Okay, that's one type of problem that we can do now. I'll tell you a lot more about this. I just wanted to show you the cool picture and get you kind of primed for thinking about, in this lecture we're going to be talking about continuous Fourier transforms, but I want you to be thinking about Fourier transforms on discrete arrays of numbers, maybe 128 by 128, and what that would look like. Okay, so let's get started. Okay, so there's a few things to do today. Okay, so in the last lecture, I told you that sines and cosines are not quite enough by themselves. right? I can use sines to approximate odd functions, cosines to approximate even functions. But if I want to approximate any function, I need more than just sines and cosines. And so I introduce these functions e to the I n x. Okay, so these have a cosine and an imaginary, a cosine and an imaginary sine part. And if I, and I might have some coefficient out here. And this could be a complex coefficient. Okay, so these are going to serve as a basis. These serve as a basis for periodic functions on the interval 0 to 2 pi. Okay, so any periodic function that you can name that doesn't blow up catastrophically to infinity, we can write as an infinite sum of these basis functions. Okay? We also have e to the 2 pi nx over L. This is a basis for 0 to L. Right? If I have a function defined on some other interval that's not 0 to 2 pi, I just rescale all of my frequencies by 2 pi over L. Okay? I'm just changing space. I'm redilating space to be in this interval instead of this interval. Okay, and remember, this L2 of 0L is just fancy notation for any nice, well-behaved function that doesn't integrate to infinity over this domain, whose square doesn't integrate to infinity over this domain. Okay, so I said that these serve as a basis for an infinite dimensional function space. There's infinitely many of these basis functions, right? One for every possible n equals 1, 2, 3, up to infinity. So one thing I want to show you is that, let's call these phi of n. So the nth function is this. So I want to show you that these phi of n serve as an orthogonal basis. They're not just a basis, but they're actually orthogonal to each other. Okay, so phi n is an orthogonal basis. Orthogonal? Sure. Oh. So what does it mean for a basis to be orthogonal? What does it mean for x, y, and z to be an orthogonal basis? What does it mean to be perpendicular? Zero inner product. Orthogonal just means perpendicular. It's a fancy word for perpendicular. And having zero inner product is how we quantify whether things are perpendicular. Okay? So this basis is orthogonal. All of these functions are orthogonal to each other if their inner products are 0. Okay? So let's just recall what our inner product is. So what is the inner product of phi m, the mth mode, the mth function, with phi n? What is this function inner product that we defined last time? How do I measure how close two functions are? The integral of the product, and one of them has to be conjugated. Okay, so it's the integral. I'm going to do it from minus pi to pi, but you could do it from 0 to 2 pi or 1 to 2 pi plus 1. It doesn't matter. Of phi m times phi n conjugate dx. Right, that's our inner product. This will tell me how close these two vectors are. And so I'm just going to plug these in. That's integral minus pi to pi of e to the I mx. What's the complex conjugate of e to the minus I nx? What's e to the I n x? That's just cos nx plus I sine nx. So the conjugate, e to the I n x conjugate, is cos minus I sine. And the only, like another way I could get that is by saying that's e to the minus I n x. Okay? So the complex conjugate of phi n is e to the minus I n x dx. This is actually really simple calculus. Okay? If I multiply these two functions, I know how to multiply exponential functions. I get e to the I x times m minus n. I'm integrating this with respect to x. And so this is basically a constant times x in the exponential. My constant times x. So the integral of that is 1 over the constant, 1 over I m minus n, e to the I m minus n x, evaluated from pi to minus pi. Okay? Okay, so what does this equal if m is not equal to n? If m is different than n, what does this equal? Right, so this equals 0 if m is not equal to n. I'm trying to think of the best way to explain why this is not equal to 0 because it's not obvious to me. Does anyone know why this is not equal? Why this is equal to 0?
The cosines will be cancelled out
because cosine of positive pi is the same as cosine of negative pi, so they cancel.
And the sine of something times pi will be 0. So
the sine of pi anything will be 0. So the sine parts are just 0. Perfect. Okay, so this is 0 if m is not equal to n. You can expand this out in sines and cosines and verify. What about if m is equal to n? So if m is equal to n,
it's e to the ix.
yeah, so
It's just 1 over I, right?
this is complicated.
well, if you go back, you can just look at the integral right now. It's still in 1.
Okay, so this will be equal to 1.
Yeah.
This integral will be equal to 1, so this integral will have to be 2 pi. Good. Okay, excellent. Thank you. So what we have is that these functions for different m and n are completely orthogonal in this L2 inner product. And when m is equal to n, they're in the same direction, obviously. Phi n is in the same direction with itself, and it has an inner product with itself of 2 pi, which means that its length is square root of 2 pi. Right? The norm of any of these vectors is root 2 pi. Okay, so this is great. What we have is an orthogonal basis, an orthogonal function basis. These are basis directions. These are vector directions that are orthogonal to each other. We have infinitely many of them. And we can essentially write any function we have in this interval 0 to 2 pi or 0 to L. We can write them in terms of these basis functions. Okay? So let's go a little bit deeper. So how do we change coordinates in 2 space? Let's just draw a picture as an analogy. So I really like analogies in 2 space and 3 space because we understand them. Okay, so let's say I have my x unit vector, I have my y unit vector. And let's say that I'm going to have a different coordinate system u and v. Okay? And I have some test vector. I'm going to call it f because f could be a vector or a function or whatever. I have some vector f. Okay, how do I write this? So the great thing about vectors is that they're purely geometric. They don't care what coordinate system I'm in. If I have the vector between me and my coffee cup, the most important vector in this room, doesn't matter what my coordinate system is. It doesn't matter if I'm in x, y, and z, or x, y, and z, or if I turn over on my side. It doesn't matter what the coordinate system is. There's still a real geometric vector connecting me to my coffee cup. But I can always take that vector and I can write it in a coordinate system. So how would I do that? How would I write f in the coordinate system of x and y? Okay, so I could take cos of the angle, sine of the angle, but I don't know what the angle is. What's a more intrinsic definition of how I could get in the x and y directions? Yeah, so I want to break it down so that I want how much of f is in the x direction and how much of f is in the y direction. How do I find those numbers? The dot product, right? So I have f is equal to the inner product of f with the x vector in the x direction plus the inner product of f with my y vector in the y direction. This is how much of my x is in this direction. How much of f is in this direction is just, this is inner product of f with x. And how much of f is in this direction is inner product of f with y. Okay? So I have this coordinate representation of my vector f. What if I want to represent my vector in UV coordinates? How do I do that? So just first of all, what does f look like in UV coordinates? So in UV coordinates, I have a minus v, right? Like I'm in the negative v direction. And I have a pretty large positive u direction because I'm well aligned with u. I have a pretty large inner product with u. Okay, so what is f in my UV coordinates? F dot u, f inner product u, in the u direction.
F dot v.
Plus f dot v in the v direction. Okay, I use these brackets because sometimes it's confusing to put a dot. Like sometimes if I just put a dot between two functions, you might think I'm multiplying them. So I want to be explicit that I'm doing this fancy special inner product. Okay, does this make sense in 2D? I can write my vector f in any orthogonal coordinate system I like in 2D, as long as I take the inner product of f with respect to those coordinates, and I write those coefficients in those coordinate directions. That's how we change coordinates. Okay? So we can do the exact same thing. A Fourier series is just a coordinate transformation into the space, into the coordinates of these phi and basis functions. Okay, so let's write this down. And I would strongly encourage you to actually start coding these up like we did on the Laplace equation for the rectangle and start trying to take your favorite functions and actually compute these coefficients and compute these Fourier transforms by hand. We can compute all of the integrals. We can compute these inner products, see how good these functions approximate using sums of e to the I n x's. Okay, so a Fourier series is just another change of coordinates. Okay, a Fourier series is a change of coordinates, or a change of basis. That's another way of saying it. A change of coordinates, or a change of basis of a function. So now we have a function f of x. Instead of our vector f, we have this, I'm calling this an infinite dimensional vector, a function f of x. Has infinite degrees of freedom. It could have any value you want at any location in x. So a Fourier series is a change of coordinates of our function f into an infinite dimensional orthogonal function space. Into an infinite dimensional orthogonal function space. spanned by these sines and cosines. Spanned by phi n equals e to the I n x. Okay, so let's do this. How would I take my function f and write it in these coordinate systems? In this coordinate system with these orthogonal basis vectors. So let's write what I want. So f of x is going to equal okay, so I'm going to take the inner product of f with respect to each of my basis vectors. So I want to write this explicitly. This is a function of x and phi of x. And our inner product is integrating these things. And this inner product tells me how much of f is in this direction. How much of f is this cosine and sine frequency. So times phi n of x. And just like in this example in 2D and 3D, I add up the contributions to each of those directions. So I have a sum on this. So I have a sum over n from negative infinity to infinity. Because I have, these n's could go from negative infinity to infinity. That's it. This is my Fourier series. This is exactly what we derived before. If you write this down, you'll see that this is exactly what we've been writing down in the last 3 lectures. This is just an integral of f in cosine and sine directions times cosines and sines of those frequencies. Okay, this is a good time to stop for questions. I'm going to write this down explicitly. So this is a good time for you to ask questions. Anyone? Yeah.
Do we always have to sum from negative infinity, or will those ever be repeated, or?
So that's a good question. This is general for complex valued functions. I could have f of x equals some complex number. If f of x is a real valued function, then we know that these coefficients will be the we know that for real valued f of x, our coefficients c of minus n, negative n coefficients, are equal to the complex conjugates of our positive n coefficients. So c minus 5, the minus fifth coefficient, is the complex conjugate of the fifth coefficient. We derived this in the last class. And so that would allow you to take this infinite sum and write it as a sum from n equals 1 to infinity of, 2 terms. And a lot of stuff would cancel out. It would actually simplify. And you'd have an n equals 0 term, which is just a flat, like the DC component or the no frequency component of the function. Okay, other questions? Okay, good. So the analogy between a 2D change of coordinates and an infinite dimensional change of coordinates, the math is actually identical. Nothing changed. But let's start thinking about what this actually means. So if we wrote, let's just do this for real valued functions, because I think this is important. And this might not be absolutely correct. I might be off by a constant, but I'll give you the general idea. And this is not in the notes. So if f of x is real valued, then this becomes even a little bit simpler. So we have f of x equals some constant plus the inner product of f of x with cos n x in the cos nx direction, plus some inner product of f of x with sine nx in the sine nx direction. And if we wanted to be really fancy, we would say this equals an, this equals bn. We have an equals integral minus pi to pi of f of x cos nx dx. And bn equals integral minus pi to pi of f of x sine nx dx. And I'm pretty sure this is a naught over 2, where a naught is just this integral with 1s here. Okay, so this is exactly what we've seen before. We wrote this exact same expression down a bunch of times. We wrote this down when we solved the Laplace equation on a rectangle. We also wrote this down in the first lecture on Fourier series. So this is the Fourier series for real valued functions that we're used to. And this pops out of this expression when you make the restriction that f is real valued and you have these, this relationship of these complex coefficients. That's exactly what you get out. Okay, so in practice, what do we do if we have a new function? So step 0, I have a new function. How do I compute its Fourier series? Sorry? I change its coordinates. How do I actually do this? Like in a computer or by hand? What do I actually do if I have a new function f of x and I want to compute its Fourier series? What do I do? Yeah, I would do some kind of a for loop either in my computer or by hand. You know, I would do the for loop. And I would basically write down these integrals and I'd try to solve them. Okay, so step 1 is solve the inner product of f with cosine and the inner product of f with sine, which means solving integrals, i.e. solve integrals. Now, a lot of these integrals I can solve by hand, right? Like, I know how to integrate cos of nx times lots of stuff, right? We've been good at integrating trigonometric functions for a long time. Let's say that I can't solve it analytically. Then I would just do it in a computer, right? I can literally add up f of x times cos of x times dx for a small dx from minus pi to pi. Super easy. I can by, with a computer, I can approximate these. So we either do this by hand or we approximate with a computer. And once we have these ANs, that's everything. We have the whole function. We can approximate this function in terms of sines and cosines. So step 2 would be, reconstruct f according to this function. Okay, so maybe a better question is, why would we want to do this? This seems like a huge hassle. I have a function f of x. Let's say it's x squared. Why would I ever want to write it in sines and cosines? So, yeah. Right, so I want to take this function and I want to break it down into its frequency components in space. Like how much low frequency, how much high frequency, what's happening in this function. Why might I want to break it down into frequency components? How many of you know what I mean when I say break it down into frequency components? How many would like a picture? Okay. So remember when we did this in the computer, we did a Fourier transform, a Fourier series for a step function. And that Fourier series for a step function, we kept adding up higher and higher frequency sine waves. Remember we had this function and our Fourier series kind of did this. And the more and more frequencies we added, the better the agreement got. Okay, so what we would like to think is that maybe I can write this function as some average value plus some, I don't really know how to draw this very well, plus some single frequency sine wave plus sine of 2 pi plus sine of 3 pi okay, and so on and so forth. Sine of 4 pi, 5 pi, 6 pi, 7 pi, and forever. And if I get the right coefficients of these sine waves and I add them all up, I might actually be able to reconstruct this shape. It's not even that crazy, right? I can almost start to see it. Like, I definitely need this average because this thing has an average. And I might want to add this, single sine hump because this thing has a big bump in the middle. But then I need this kind of sine of 3x, a negative one of those, to cancel out the part of the hump that's out here. And I might need a sine to the 5th and a sine to the 7th. So I might have an odd sine sequence to approximate this function. Let me show you something like just in Wikipedia has a really good visualization of this, actually. Okay, so this is a pretty good visualization. This is my step wave, my square wave approximated with 1 sine, with 2 sines, 3 sines, 4 sines, and so on. It just gets better and better the more of these sines you add. And there's this great visualization here. Okay? Let's see if I can make this bigger. I don't know how to restart this movie. Okay, so you can see kind of these shaded blue sine waves of different amplitudes approximate this square wave. And if you add them all up, they're each individual sine waves of their own frequency. But if you add them up in the right proportion and the right Fourier coefficients, these are my inner product of f with my sines. If you add those single frequencies up with the right proportions, you can approximate almost any function. Okay? Are there questions about this? This is a pretty important concept, and it is also a little bit abstract and possibly confusing. Any questions about this idea of changing coordinates into these sines and cosines? Yeah.
I guess what are the coefficients you were talking about? Like to weigh which one is more?
Yeah, so these are the coefficients that tell me how much of cosine of, a higher frequency cosine wave is cosine of 100x versus cosine of 1x. Cos of 1x is a slow cosine. Cos of 100x is, really rippling a lot. And this inner product tells me how much of that really high frequency cosine I need versus how much of the low frequency cosine I need to approximate this function. And in general, I'm going to need cosines and sines to get any arbitrary function, unless they're odd or even. Okay? So one of the reasons I might want to take a function and break it down into these sine and cosine components is because in my linear partial differential equation, so I have a linear PDE like UTT equals K UXX. This is the partial differential equation for a guitar string. Okay, so let's say I take my guitar string and I pluck this guitar string. This is a linear partial differential equation. And maybe if I pluck it, I actually pull it down so it looks kind of like that. It's a triangular wave initial condition. It's not anything nice. It has all kinds of frequency components. But when I let this thing go, what I can do is I can say, well, what does this PDE look like for this single frequency sine wave? And what does it look like for this single frequency sine wave, and this one, and all of them? And it turns out that these sine waves, when you plug them into this PDE, are really simple. Right? If I take uxx of a sine wave, I get minus a sine wave. Okay? And so I can essentially get an ordinary differential equation for the coefficients of each of these sine waves. And because this system is linear, I can solve each of those pure tone PDE problems individually, and then I can add them all up at the end. So Fourier transforms are going to allow me to solve difficult PDEs in the frequency domain. So I'm going to solve how does this partial differential equation change my frequencies. And then I'm going to be able to recombine them and figure out what my actual shape is on this guitar string. Okay, so that's why we're doing Fourier transforms in the first place, is because they simplify our partial differential equations a lot. Lots of PDEs are much simpler in the frequency domain, in the Fourier transform coordinates. That's why we change coordinates ever. Like, the only reason we would ever change coordinates is if it makes our lives simpler. Okay, we change to polar coordinates when we have some kind of axisymmetry. We change to spherical coordinates when we're symmetric in a sphere. We change to Fourier coefficients when it makes our partial differential equation simpler. So what we're going to find is that if I write my function u as a sum of sines and cosines, I can take my PDE and I can get n super simple ODEs out. And I know how to solve ODEs. Okay, that's why we're doing this in the first place. Okay, any questions before I go further? How many of you feel somewhat comfortable with this? How many of you do not feel that comfortable with this yet? It's okay, you don't have to. It's going to become a lot clearer why we care about these things when we start solving PDEs. It's also going to become a lot clearer why writing a function in terms of these sine waves is nice. And all of this Fourier transform coordinate change stuff becomes super simple when you do it in a computer. When you do this on a discrete domain on vectors in a computer, to me, it makes way more sense. Okay? But I want you to know the full theory, because it's very, very, very important. Okay, so we have a Fourier series. And it allows us to approximate lots of functions that we care about. So if I have a function like that square wave, I'm able to approximate this function really well. Let's say this is between 0 and L. But what is my basic assumption in Fourier series about these functions from 0 to L? They're periodic. And so what I'm actually simulating, what I'm actually representing, because these sine waves don't just stop at L. They keep going and they have, more stuff forever. Positive x to infinity, negative x to infinity. So really, I also have all of this other crap that is being represented by my Fourier series, and I might not want all of that other stuff. I might actually have a function which is just a square wave and then nothing else to infinity. And my Fourier series does not capture that. My Fourier series, by definition, is going to force repetition for every 2L, 3L, 4L. Okay, so my Fourier series does not allow me to represent all functions on the entire domain. It only allows me to represent periodic functions, purely periodic. So the most important generalization of the Fourier series is something called the Fourier integral transform. So I'm sure most of you have seen the Fourier transform at some point written as a big integral. And that's what we're going to write right now. And the Fourier transform, this integral, is actually what's the most useful for partial differential equations. Okay. So how do I want to do this? Okay, so we're going to take our Fourier series on minus L to L and take the limit as L goes to infinity. So we're going to define this for functions minus L to L, and then we're going to take the limit as those goes to infinity, and we'll be able to represent any function. Right, so we had our f of x equals a naught over 2. I shouldn't have erased this. Sum n equals 1 to infinity of a n cos n pi x over L plus b n sine n pi x over L. These coefficients a and n are just the inner product of my function with these basis functions. Okay, just inner product. I could write this as 1 over 2L sum from minus infinity to infinity of f of x inner product with phi n of x in the phi n of x direction. Totally fine, that's the change of coordinates. And so f is represented as an infinite sum of sines and cosines with frequencies. These are kind of discretized or quantized frequencies given by omega n equals n pi over L. Okay? Okay, this is just summarizing everything we've done over the last 2 or 2.5 lectures. So we're going to write down this Fourier series from minus L over 2 to L over 2, or from 0 to L, or I guess from minus L to L. And we're going to take L as it goes to infinity. I really need a better black pen. Okay, so if we take L goes to infinity, I'm going to define omega equals n pi over L, and delta omega is just pi over L. So these are kind of my delta frequency elements. I keep increasing my frequency by these increments. And we're going to take the limit as L goes to infinity, which is the same as the limit as delta W goes to 0. I'm going to make my frequency spacing infinitesimally close. Okay, so if I have f of x equals the limit as delta W goes to 0 of that infinite sum there. So I have this sum of minus infinity to infinity. My inner product term, my coefficient, I'm just going to write this out explicitly. It's WL over 2 pi integral from minus pi over delta W to pi over delta W of f. I'm going to tell you what I'm doing here in a minute. This is a long, shitty expression. Okay. This is just L and minus L. This is inner product of f with phi n, right? This is phi n. This is f. I'm integrating from minus L to L, and I just have some dummy variable that I'm integrating with respect to so that we don't get confused. So I have the inner product of f with this basis function times this basis function. Okay, that's what we have. And this whole formula here, we're going to define as, if we take the limit as delta W goes to 0, this is the integral from minus infinity to infinity of f of c e to the minus I n I omega c. And this is the definition of our Fourier transform. That's it. That's the Fourier transform. This is the definition of my Fourier transform. Okay, so let's think about how to interpret this. We can write our function as an infinite sum of basis functions, and these are the coefficients of those basis functions. So my Fourier transform is essentially just the coefficients of these frequency components. And I take the limit as delta W goes to 0, so that my domain, instead of from negative L to L, it goes from negative infinity to infinity. I'm taking the limit as my domain gets infinitely large. And these coefficients, these are just my Cn. These are just the Cn from before. But I've taken the limit as my domain goes to infinity. And we call this f hat, and it's a function of omega. I'm integrating this C out, and I just get a function of omega. And omega is my frequency. It's the frequency of the sines and cosines. So my Fourier transform are how much of f are in each of those sine and cosine directions. How much of that, for a given omega, how much of f has that sine and cosine of omega in it? Okay, so why did we go from Fourier series to Fourier transform integral?
Generalize it for non-periodic functions.
We want to generalize this for non-periodic functions. I want to be able to have a function that does nothing and then does some stuff and then does nothing again. And I don't want to constrain it to be periodic. So I want to take the limit as L goes to infinity. And when I do that, instead of just discrete coefficients C1, C2, C3, C4 for the, each of these modes, I have a whole function of omega. So before I had, C1 is the coefficient of, my basic first period sine wave. And C2 is the coefficient of my second sine wave, and so on and so forth. I had just countably infinitely many. I had 1, 2, 3, all the way up to infinitely many of these coefficients. But when I took the limit as L goes to infinity, the spacing between my frequencies went to 0, and instead of discrete frequencies, I have a continuum of frequencies. I can have every frequency between here and here. I have an entire function of all frequencies. I can plug in 2 pi or 2 pi plus 0.0001. I can plug in any frequency I like here, and I can tell how much of my function is in that exact sine or cosine frequency. It's a little weird. Okay, this is going to take some time to digest. I don't expect this to be super obvious at the beginning. But what I'm getting at is that this Fourier transform that almost all of you have seen before, just maybe defined, this is the generalization of a Fourier series. This is just a way of saying we're integrating, we're adding up a bunch of sines and cosines in this amount. We're adding, our function is just the sum of a bunch of sines and cosines in this amount. Each of those sines and cosines has this coefficient out front. Okay, we're going to learn more about this. We're going to look at properties and generalizations and how we can use this for partial differential equations on Monday. Okay, the final is due today at 5 under my door or in hand. Have a great weekend. Thank you.